You know, deep inside every single electronic device you own, from the phone in your hand to a satellite orbiting Earth, electricity is following this strict set of hidden rules. It's not some kind of magic, it's just physics. And today we're going to decode them together.
So how does electricity navigate that incredible maze of wires? I mean, it doesn't just get lost, right? Well, it turns out it follows a surprisingly simple and, well, elegant set of rules that act just like a map. And today, we're going to learn how to read it.
All right, so we're going to start with the most famous rule in the book. This is the one that really forms the foundation for almost everything else when it comes to analyzing circuits. And that is, of course, Ohm's law. Okay, first things first, let's meet the key players. Now, the easiest way to think about this is to imagine electricity is like water flowing through a pipe. In that system, voltage, that's the V, is the pressure. It's the force, the push, that gets that electric charge moving in the first place. I mean, it's simple, right? No pressure, no flow. So if voltage is the pressure pushing the water, then current, that's the I, is the actual flow of the water. It's how much electric charge is moving past a certain point every single second. And really, this is what we're usually trying to control or use in a circuit. And finally, that brings us to resistance, or R. This is basically anything that gets in the way of that flow. So sticking with our water analogy, this could be a really narrow section of the pipe, or maybe even a plug. Resistance works against the current, slowing it down. So you can see the relationship between these three is actually pretty intuitive when you think about it like that. You get more pressure, that's more voltage, and you get more flow, which is more current. But if you add more friction, more resistance, well, the flow slows right down. It's all just a simple balancing act. And this is exactly what the German physicist George Simon Ohm figured out way back in 1827. He was the one who first put the math to this crucial relationship, and his discovery, well, it became the most important early description of how electricity really works. And this is it, the simple but incredibly powerful equation that ties it all together. You see these three variations? With them, if you know any two of the values, voltage, current, or resistance, you can always figure out the third. This is our number one foundational tool. But here's the thing. Ohm's law is great for simple, single-loop circuits. So what happens when things get more complicated? You know, with multiple power sources, branching paths, a real labyrinth of wires? Well, for that, we need a more advanced rulebook. And that comes to us courtesy of a guy named Gustav Kirchoff. So Kirchhoff gave us these two brilliant laws that, together, let us analyze pretty much any circuit, no matter how complex it looks. The first one, it's all about current at a junction. The second is all about voltage in a loop. You can really think of them as the conservation laws for electricity. Okay, let's break down that first law, the junction rule. I want you to look right at that point J1, where the wires meet. You see the main current, I, flowing in? Well, it gets to that junction and it has to split. It can't just, vanish. So the current flowing out through I1 and I2 has to add up to exactly the amount that flowed in. It's that simple. What goes in must come out. Now, the second law, the loop rule. This one's kind of like a roller coaster. Just think about it. You start at the bottom, right? The chain lift, that's our battery, hauls you up, giving you a huge boost of potential energy or voltage. Then, as you zoom through the twists and turns of the track, those are our resistors, you lose that energy. By the time you pull back into the station, you're at the exact same height you started. That's the loop rule, in a nutshell. In any closed loop, all the voltage you gain from batteries is perfectly balanced by all the voltage you lose in the components. The net change is always, always zero. All right, so we've got our rules, we've got Ohm's law, we've got Kirchhoff's two laws. Now let's put them to the test and become circuit detectives. We're about to solve a puzzle using all of these laws together. Okay, here's our target. This is a circuit with two batteries and two resistors, and as you can see, it is not a simple loop, so Ohm's law by itself just isn't going to cut it here. Our mission, should we choose to accept it, is to figure out exactly how much current is flowing through every single part of this thing. The absolute key here is to be systematic. So first, we're just going to label everything. We'll make a guess on the direction of the currents, and we'll label our loops. Then we apply Kirchhoff's laws to turn this picture into a set of algebraic equations. And finally, the fun part, we solve those equations to find what we're looking for. And this is where the magic really happens. Just by tracing each of those loops and applying the voltage law, remembering that batteries add voltage and resistors spend it, we can write down these two equations right here. What we have now is a system of equations that describes the entire circuit. Now, if you look at the equation for loop A, it's actually pretty nice and simple. It's only got one unknown current, I1. So a little bit of algebra, and boom, we've got our first clue. We now know that the current flowing down through that middle resistor is 0.015 amps. Okay, so now we take that value for I1, we plug it into our second equation, and we solve for I2. And what we get is, wait a minute, a negative number? Whoa, hold on a second. A negative current? A negative flow? Did we mess up somewhere? How can you even have less than zero current? You know, this is a really common point of confusion for people, but honestly, it's also one of the absolute coolest parts of this whole method. See, that negative sign? It's not an error, not at all. It's the math literally telling us something important. It's saying, hey, your initial guess for the direction of that current, it was backwards. The current is simply flowing in the opposite direction. Isn't that amazing? The method is self-correcting. We don't even have to guess right at the beginning. The physics just sorts it all out for us in the end. So that's a pretty neat trick for solving a circuit puzzle, right? But I want to be really clear. These aren't just some dusty old textbook rules from the 19th century. In fact, they are more critical today than they have ever been before. I mean, just look at this quote from a research paper from this year, 2024. It says it all. The simple DC circuits, just like the ones we've been looking at, are the fundamental building blocks for the massive networks that are going to power our future. Understanding this stuff is absolutely central to the global energy transition. Just think about it for a second. Solar panels, batteries, all the electronics in electric vehicles, they all run on DC power. So to build stable, efficient power grids that can handle gigantic offshore wind farms or manage entire fleets of electric vehicles, what do you think engineers use? They use these very same fundamental laws, Ohm's and Kirchoff's, to design and simulate the complex power networks of tomorrow. So the next time you plug in your phone, just take a second and remember the hidden rules that are at play inside. The very same logic that balances a tiny circuit like the one we solved is what engineers are using right now to balance an entire national power grid. These 200-year-old laws, they're not just history. They are the fundamental language we are using to design our entire electric future.